We are moving on with Unit 3. This unit is not done. We are only about halfway over, but not even yet. So, unfortunately, we're going to just keep trucking along. 3.7 is about solutions and mixtures. So, solutions are sometimes also called homogeneous mixtures. And they can be solids, liquids, or gases, but most often we deal with liquids. In a solution, the macroscopic properties do not vary throughout the sample. In a heterogeneous mixture, the macroscopic properties do depend on the location in the mixture. In heterogeneous, you can tell the difference. But like when you have a solution of Kool-Aid, you can't see the difference. So that would be a homogeneous mixture. Chemical reactions often take place when two solutions are mixed. So to form stoichiometric calculations, we must know two things in order to solve them. We need to know the nature of the reaction and the amount of chemicals present in the solutions. So some other words from Chem 1, when you have a solution, the solute is the thing that's being dissolved, and the solvent is the dissolving medium. And water is the universal solvent, and we're going to talk about that in the second half of the unit. Actually, I think that's 3.9. Molarity is the most common way to express concentration. So anytime I say concentration, it's probably going to be molarity. Molarity is defined as the moles of solute per volume of solution in liters. So that is the key to know that the solute is the only thing on top, but the resulting solution goes on top or on the bottom. Because when you add your solute to your solvent, like if you have 100 milliliters of water and 20 grams of salt, and you're adding them together, the volume is no longer going to just be 100 milliliters. It's going to be more than 100 because the solute takes up some volume space. So that's something that we have to be careful about when you're reading problems. You're putting in the right values for that. Okay? But let's practice with this equation because, you know, we need to. A solution that is 1 molar is written as 1.0 m, contains 1 mole of solute per liter of solution. So not only can we just use the molarity equation, molarity equals moles over liters, but we could also use it as a conversion factor. I personally would rather use it as a conversion factor, but it's up to you which way you would like to do it. Okay, so we want to calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide to make 1.50 liters of solution. Okay, so what are we solving for? Molarity. That's the big M, right? Okay. I know liters is which one? Liters, right? Yeah. Can I just plug in the 11.5 grams for moles? No. We have to switch it to moles. And how do we switch it to moles? We're going to divide by molar mass. Yep. If grams are here, we put the molar mass in the bottom. And what is the molar mass we need to find of? Sodium hydroxide. So you have to look for that species in the problem to know what is the substance that you're going to find it. So anybody know what sodium hydroxide is off the top of their heads?
22.99 plus.
It's NaOH.
Plus 1.
Yep. So
24 plus 6. So 40. About 40.
23 plus 16.
0.99. 22.99. Or no, yeah, 22.9.
So that's about
40.
40. If you want to be exact, you are more than welcome to be exact. I know the periodic tables that you use for the AP exam have less decimals in some cases. It is exactly 40 when you use those decimals? Okay. I used a different periodic table and I got 39.997.
Yeah, exactly.
So it should be the same. It doesn't matter, right? Really? Okay. So when you divide those, what do we get for moles?
0.2875.
Thank you. Okay. And then now to find molarity, what are we going to do with that number? Because that is not molarity. Yes. Now we have to divide by the volume to get the molarity. So we would just take the 0.2875 divided by 1.50. What if I gave you in milliliters? Could I just use milliliters, or do you have to change it to liters? Has to be liters. Just capital M for molar for the unit on molarity.
You forgot to put the mole over on the left side.
Thank you. And the answer is? And this is a Chem 1 question. When you read the M, what's it actually called? Molar. Like your tooth. Molar, like your tooth. Not molarity. Molar, like your tooth. Okay, so pretty simple stuff. Hopefully, it's a nice quick refresher of Chemistry 1, how to solve for molarity. Okay, now I unfortunately didn't realize that for some reason it printed weird. I didn't go back and check that. But for example 13, give the concentration of each type of ion in 0.5 molar cobalt-2 nitrate solution. Okay, so just like how when you have a balanced chemical equation and we use a mole ratio to do that, we can figure out mole ratios based on the number of ions present in a compound in order to change molarities. So the first thing we need to do is we need to write the formula for cobalt-2 nitrate. What's the symbol of cobalt? CO. And that Roman numeral means what? Plus 2. Does anybody remember nitrate? NO3 -1. Close. Okay, so then what's the formula of that going to be? Yep, we put NO3 inside parentheses and then a 2 on the outside. Okay, so from this formula, correctly written, we can see that how many cobalt ions do we have? Just one, right? There's no subscript, so we know that there's one Cu, or CO plus 2. And then how many nitrates do we have? 2. You could break it down into N's and O's, but we want to know the concentration of each type of ion. And so the only 2 ions involved are the cobalt and the nitrate. Okay? So what we're going to do with the 1 and the 2 is we're going to multiply the molarity that we're given by the number of ions present, and that will give us the molarity of the ions. So for cobalt, it's just 1 times the 0.50, so that's going to be the same 0.50 molar for cobalt ions. But for the nitrate, we have to take it times 2. So 0.5 times 2, rounded to correct significant figures, would be what? 1.0. 1.0 molar for the nitrate. So that tells us that there's twice as many, the concentration is twice as big for the nitrate, and that's because there's twice as many ions. For every 1 cobalt, you have 2 nitrates involved. Okay? So this is just something a little bit different that we didn't do in Chem 1, but it can still relate to molarity in this way. And we're going to do this a lot this year. All right? And example 14, which, by the way, these examples just continued numbering from the first round of numbering. So we go up to example 24 in this round. Calculate the number of moles of chloride ions in 1.75 liters of 1.0 times 10 negative third molar zinc chloride solution. So this kind of just ties in both that we just did in 11 and 12 and 13 together. So what should we do first? Gotta do what? What should we do first? What do we have? So we're given the volume, right? So we know from our molarity equals moles over liters, we know the liters. And then the 1.0 times 10 negative 3 m is the molarity. We want to know moles, but this moles is the moles of the whole thing, which I just gave it to you without even thinking. Zinc has a +2, chlorine has a -1, so zinc chloride is ZnCl2. Okay, but we don't want the moles of the whole thing, we want the moles of just the chloride ions. So we have to solve for the moles of the whole thing, and then we're going to multiply by the ratio of chloride ions in the zinc. Okay? So now I'm going to do it this way so I can show you how you can use the molarity as a conversion factor. But then in the future, you can do whatever way works for you. So since I know molarity is moles per liter, per 1 liter, what I do is I start with my liters. I take 1.75 liters over 1. And then I set it up so that I put the molarity in the numerator. And that's how many moles are in 1 liter of that solution, like that. And so you would still mathematically multiply the two numbers if you use the equation. But for me, it's just easier to do it this way, especially if you're just continuing on with dimensional analysis. But it's a personal preference thing. So the moles are going to be 1.75 times 10 to the negative 3 moles. And that's the moles of the zinc chloride. I know my CV's okay, but this isn't the answer. We need to have moles of just the chloride. So, thinking back to what we did in example 13, how many chloride ions are there present in the full compound? 2. Because if zinc chloride is this, for every 1 zinc chloride, we have 2 chloride ions because of the 2 there. So what we'll do with this mole, and so like, if I was just doing this by myself and not showing you, then I would have actually not stopped. I would have just kept going. Where I would then, so this is moles of zinc chloride. I know that for every 1 mole of zinc chloride, we have 2 moles of the chloride ion. So you just multiply by 2. And that final answer, which I'm not facing this correctly, 3.5 times 10 to the negative 3rd moles of chloride ion. Anybody confused about where that came from? All right. So those are just some of the ways that you might solve using molarity. There are more than that. Like, I'll probably throw in density at you. Density is mass per volume, so correlates very nicely with moles per liter with that. But we're going to keep going. We're going to example 16. Okay. Do we get it if I move on? A standard solution is a solution whose concentration is accurately known. So we will do a lab this year where I actually standardize a solution. Instead of saying like 0.1 molar sodium hydroxide, I'll say that it's 0.09370. Like I'll go to a lot more decimal places. So a standard solution, we just know more accurately to more decimal places what is the exact molarity of that. And what this picture shows is these are called volumetric flasks, where, and we have some, and we'll use some in this class, but if you fill to the line, then it is exactly a certain molar, or a certain volume. So like if you fill it to the line, it'd be exactly 100 milliliters kind of thing. And so if you ever were trying to standardize, then if you got to that line and got exactly that amount, then that gives you correct significant figures to get to those decimals. So we'll do that later in the lab. But when we're using those, sometimes we make what are called dilutions. So we use this equation in Chem 1 where sometimes we need to add some water to a stock solution to achieve a more dilute concentration. So the 1s and the 2s are related to each other, and I have to do this a lot when I prepare stuff for you guys. So the numbers of moles are equivalent when the dilution occurs. Now, does it matter if you plug in liters versus milliliters for the volumes? No, because the moles are equivalent, and as long as you have the correct unit for volume on either side, it doesn't make a difference. So I would say don't do more work than you have to. Okay. So example 15, what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.10 molar solution. So the hardest part here is plugging in the correct spots and relating. So remember some key words. If it says of, that means the two numbers that are separated by of are related. Okay? So that tells me right away that the 1.5 of 0.10 molar, those are both related. So do you guys want those to be the ones or the twos? Twos. Okay. So I'm going to put 0.10 molar for M2 and 1.5 liters for V2. If you did it the other way, it's okay. So then that means the other molar is going to be M1, and we want volume of that, so that means that the V1 is what we're solving for. Okay, so then we have 16 times V1 equals 0.10 times 1.5. A little bit of math magic. What do you guess? 0.0094. If you would like to put that in scientific notation, you could. So like 9.4 times 10 to the negative 3 liters. Or we're not going to be adding that in liters to our solution. Instead, we'll probably add it in milliliters. So that would be 9.4 milliliters. That makes more sense. So what that means is when I concentrated sulfuric acid is 16 molar. And that's the stuff that like eats through my pants when I do that, and like the year that I burned my face with acid, it was this acid. But so to make this solution, I would take 9.4 milliliters of sulfuric acid and add it to water until I prepared 1.5 liters, sort of thing. I would actually probably try to find it not from the 16. I would probably take it from somewhere else because I don't want to deal with it if I don't want to. Okay, almost done. Questions about this? All right. Mixtures can have variable composition. Qualitatively, we use the words dilute and concentrated to describe the solution content. Dilute meaning there's very little solute present, lots of solvent, and concentrated to mean large amounts of solute. So a lot of this is going to be talked about throughout the rest of the unit, and how did these relate numerically to different things. But another way to describe solutions is using what's called a mole fraction. So mole fraction is signified by an x. It's actually the Greek letter chi, C-H-I, I think I say it right. But an x is fine, where it's the ratio of the number of moles given of a given component to the total moles. So the equation, and this is given on the equation sheet, that if you need to know the mole fraction of A, then you're going to put the A moles on top and then the total moles, so A plus B plus C plus whatever components are in there on the bottom. Okay, so this, I think we've done something similar to a mole fraction before. It's kind of like a percentage, but it's not times 100, so you don't have to put a percent. There's no units for this. In one lab, we did something called atom economy, which is very similar to this, this type of ratio. Okay, so no units involved because the units cancel because everything's moles. Moles part over moles total to find it. And they all add up to 1. So if you had to find 2 mole fractions for 2 different substances, if you knew one of them, then you could subtract from one to find the other one to make life simpler. A solution is prepared by mixing 1 gram of ethanol, which is C2H5OH, with 100 grams of water to give a final volume of 101 milliliters. Calculate the molarity of the and mole fraction of ethanol in this solution. So, in order to find the mole fraction of ethanol, I'm going to put just ETH for ethanol. We need to know the moles of ethanol over the moles of ethanol plus the moles. What is ethanol mixed with? Water. So we'll have to find the moles of water and the moles of ethanol in order to solve that part. But we also need to know the molarity. So to find the molarity of the ethanol, we need to know the moles of the ethanol used over the liters of the solution. Okay? So which would you guys like to do first? Molarity? Okay. So do we know the volume of the solution? Yes. So the final volume of 101 milliliters is the volume of the solution. So I'm going to just put V solution is 101 milliliters. And what would that be in liters? 0.101 liters. Right? Just move your decimal 3 times. Or divide by 1,000. Okay, but we need to know the moles of ethanol, and we know that we have 1 gram used. Do I need to also include the grams of water right now? No, it's only if it's moles of something, you only use the grams of that part. So we will take our 1 gram of ethanol, and just like we did before, to get it to moles, we will divide by molar mass. And that's why this is given. So you can find that molar mass. And the molar mass is 46.07. And I got the moles to be 0.0217. I have a couple minutes of class left, so I'm just gonna, is it okay if I just keep giving you all the answers?
Yeah.
Okay. So now that we know the moles, then we're gonna divide by liters. So we'll just take that divided by the 0.101. And that is 0.215 molar. So the solution's molarity concentration is 0.215 molar. Now we need to then solve for the mole fraction. So for the mole fraction, I know the numerator is going to be this right here, because it's the moles of the ethanol. And then the denominator is moles ethanol again, plus the moles of water. We haven't solved for moles of water yet. So that's why you're given 100 grams of water. So to find the moles of water, you take your 100 grams divided by the molar mass of water, which is like 18.015 or 18.02 grams, and the moles of water is 5.55. So then that 5.55 would go in the denominator to add to the 0.20217. So the mole fraction of the ethanol, when you divide all that out, is 0.00389. So again, 0.00389 for that. So the problems with this unit, or this section, practice mole fraction, it practices molarity, it practices like how can you use all these things together, okay?